Previously, fatigue as phenomenon has been explained with respect to the different phases one may observe. There is the initial phase, followed by a phase that represents macroscopic growth of damage. The transition between these two phases is not very strict in its definition. It cannot be quantified in dimensions of the damage. In general, the transition is considered to take place when the microscopic damage in its growth is no longer depending on the surface conditions, but rather by the resistance of the bulk material. This transition may therefore be different for the different metallic materials. Now, to understand the fatigue damage mechanisms in metals, various aspects are briefly discussed here in the order indicated on this slide. Microcracks initially extend along slip bands. Hence, the crystallographic nature of the material will initially dominate the formation of microcracks. Crystallographic aspects considered here are the type of crystal lattice and the elastic anisotropy and allotropy. The three most common crystal lattices are body-centered cubic, like ferrite materials, face-centered cubic, like aluminium, copper and nickel, and hexagonal, closed-packed, like for example magnesium. The material response depends on this crystal lattice but may still vary greatly. Take for example the elastic anisotropy, which may be substantially different even for the same lattice, as illustrated here for aluminium and copper. Slip systems relate to the crystallographic planes, but the ease of slip is greatly affected by how easy cross-slip can occur. For aluminium, this is for example much easier than for nickel or copper. From one grain to another, the individual grain size and orientation contribute to how easy or how difficult microcracks develop from one grain into the next. The illustrated variation in properties depending on the orientation seems to have some similarity with the different properties that fibers and matrix have in composites. The initiation of matrix cracks in composites is often greatly affected by the individual properties as well. The nucleation of microcracks may be easier at the free surface of a material because of less constraint, but often microcracks nucleate at inclusions in the material. In particular, inclusions in the material form a micro-level stress concentration from which a microscopic crack may nucleate. This stress concentration seems similar for any inhomogeneous material. As mentioned before, the difference between fiber properties and matrix may initiate a crack, but also the open structure of, for example, wood or voids present in the material may form a nucleation site. If such microcrack nucleates below the surface, the growth of it may perceive when observed at the surface as initially fast growing. However, this growth merely consists of breaking the ligament between the microcrack and the surface. An interesting observation made in laboratory experiments is the nucleation of microscopically small cracks that did not propagate further to macroscopic lengths. This observation was mostly done for notch conditions, where a high stress concentration caused the nucleation of a crack, which after developing over a few grains retarded. This is illustrated in the graph on the left-hand side with the non-propagating cracks. The right-hand side graph illustrates the observation for this non-propagating crack, particularly for high stress concentration factors. Cracks may nucleate, but may also terminate after a few grain diameters. Away from the free surface, the restraint on cyclic slip may alter, and hence the crack may encounter some sort of threshold for crack growth. Several types of barriers may be identified. Although grain barriers don't stop crack growth, a microcrack may nucleate within a grain, not being able to penetrate into neighboring grains. But also the two-phase barriers, such as the pearlite islands in low-carbon steel or the alpha-beta interfaces in titanium alloys, may form such microstructural barrier. Here one has to understand that the fatigue limit represented by the lower asymptote in the fatigue life or SN curve does not represent the limit on crack nucleation, but on propagation of cracks until failure. The SN curves represent failure lives. Below the fatigue limit, cracks may nucleate, but they don't grow to macroscopic lengths. As these microstructural barriers depend on the material grain structure, the fatigue limit thus also depends on the material. For steel, for example, very distinct limits are observed, while for aluminium the limit may still slowly decrease after the lower knee point. At extremely high number of fatigue cycles, failure may be observed at lower stress amplitudes than the fatigue limit. Another aspect that we should consider when investigating fatigue fracture surfaces is the number of crack nuclei. Take for example the fracture surface of a car axle failure. It seems to have a single point of origin as illustrated with the sketch on the right hand side. However, this fracture surface, corresponding to a load case of reverse bending, clearly shows multiple locations of origin. The sharp corner edge easily nucleates multiple microcracks that at some point in time link up. Because these small fracture surfaces are not in the identical plane, link up occurs with a step, which is visible as a line or a marker in the direction of the crack growth, which is known as ratchet mark. In general, high number of crack nuclei indicates high local amplitude stresses, which may either relate to high loading amplitudes or high stress concentrations or rough and damaged surfaces, for example. Hence, looking at SN curves, one may generally expect higher number of crack nuclei at high amplitude stresses, where near the fatigue limit, in the end only a single crack may have nucleated and propagated to failure. This explains also the amount of scatter observed in experimental results. High number of nuclei indicates easier crack initiation and hence less scatter. Near the fatigue limit, however, the amount of scatter is substantial. Because the initiation phase is dominated by the surface conditions, the surface aspects are very important for that phase. Here, the list illustrates that the surface conditions, but also what the environment does to the surface, directly influences the initiation phase. The growth phase is merely dominated by bulk material resistance and to much lesser extent the environment. The data on the right hand side supports this observation. Two different surface roughness conditions, a smooth and a coarse surface, clearly results in distinct initiation lives, while the crack growth lives are almost identical. One can also see this effect back in the SN curves. Comparing the fatigue life curves for smooth and rough surfaces clearly shows differences near the fatigue limit. In particular, corrosion as an environmental aspect reveals this reduction in fatigue life curves near the fatigue limit, as will be discussed later in this course. During the crack growth phase, the crack growth is determined by the bulk material and no longer by the surface conditions. The crack propagates generally perpendicular to the principal stress by a mechanism in which deformation occurs along multiple slip systems. The illustration on the right hand side illustrates a possible mechanism. The slip systems illustrated are in the location of maximum shear, and their deformation will cause the crack to increment. This slip deformation is not fully reversible due to the strain hardening, hence, during loading and unloading, little microscopic plastic ridges will be formed while the crack increments. These ridges are called striations, which cannot be observed with the naked eye, but with an electron microscope. Now, the exact mechanism of crack incrementing is not fully understood, and literature illustrates various concepts of crack growth. The illustration on the right gives a symmetric presentation of growth, while the illustration in the center proposes an asymmetric form of crack growth. Either way, the striations visible on the fracture surface are important features for fracture surface analysis. These striations differ in shape depending on the magnitude of the load cycle. This is clearly illustrated with the fracture surface on the left hand side, where a load spectrum was applied with after 10 small cycles a larger load cycle was applied. The fracture surface reveals the repetitive nature of the striations with a single larger striation related to the larger load cycle. Where the image on the left is looking at the surface from the top, looking at an angle with respect to the fracture surface reveals that the fracture surface is not perfectly flat. Although fatigue fractures are macroscopically smooth and flat, microscopically the fracture surface isn't. Depending on the load sequence, the formation of striations may come together with stepping up and stepping down on the fracture surface. In general, striations are fairly well visible in aluminium, but very difficult to see in steels or titanium. As mentioned before, the environment has effect both in the initiation and crack growth phase. In the initiation phase, corrosion can be considered in two cases. Corrosion damage is created and thereafter loading is applied in a non-aggressive environment, or an intact material is loaded while being in a corrosive environment. In both cases, damage to the surface in the end will form stress races, which may cause nucleation of fatigue cracks. The SN curves on the right hand side illustrate the effect. Water and salt water as environment reduce the fatigue properties compared to air. Another aspect illustrated in this figure is the effect of frequency. If the frequency decreases, the fatigue properties will reduce as well. At low frequencies, the load cycle is slowly applied, giving the environment more time to access the critical locations, like for example the crack tip. Hence, one has to consider the effect of the load cycle wave shape and its frequency. Low frequency and low ramp-up rates give more access to environment, while short and steep ramp-up rates reduce the effect of environment. The influence of environment should not only be limited to the medium, but also to the ambient temperature. In general, an increase in temperature reduces not only mechanical properties, but also the fatigue properties of materials. Mostly this relates to material resistance, but also the increase in thermal stresses within a build-up structure may add to the magnitude of mechanical loading. At low temperatures, the effect of temperature is opposite. Partly this relates to the reduced amount of water vapor in the air, which reduces reaction and diffusion rates. Hence, an aircraft flying several hours at cruising altitude effectively implies a cabin pressure load cycle at a very low frequency, but as it flies in a non-aggressive and cold medium, its contribution to fatigue effectively is low. Nonetheless, the image of the Concorde illustrates that when high-speed transport aircraft are considered, the aerodynamic friction will cause heat up of the structure. Hence, aluminium alloys should be considered there that have sufficient fatigue resistance at this elevated temperature. The influence of temperature is similar for all materials, including composites. Increasing ambient temperature softens the matrix, in particular near the glass transition temperature, and reducing temperature makes the matrix more stiff and brittle. The consequence to fatigue damage development is then similar to metals. The images at the bottom here are delamination shapes observed in fiber metal laminates when fatigue loading these laminates at different temperatures. High ambient temperature yield large delaminations and faster crack growth, while low temperatures result in very small delaminations and slow crack growth, as illustrated here on the right. Because cyclic slip contributes to the nucleation and early propagation of microcracks, the load case will have a substantial effect as well. Take for example the case of a bar loaded in torsion and in tension. In tension, cyclic slip occurs under an angle of 45 degrees with the actual load, while in torsion maximum shear occurs both parallel and perpendicular to the actual direction. Another difference is that the normal stress component in case of tension helps with the transition from cyclic slip to microcrack and subsequently to open that microcrack. This opening is absent in case of shear due to torsion, which hinders the formation of microcracks at low amplitude loads. If cracks initiate, they propagate perpendicular to the principal stresses, which result in the case of torsion in those spiral fracture surfaces. In general, fatigue failures in metals are characterized at the macroscopic level by the absence of plasticity, the formation of growth bands depending on the load spectrum applied, the growth perpendicular to the principal stresses, and the number of crack nuclei depending on the load magnitude, and, in case of multiple crack nuclei, the formation of radial steps or ratchet marks. At the microscopic level, cracks are observed to grow through the grains while forming little plastic ridges called striations. A practical example of those striations is given here. A fatigue failure of a flap beam of a civil transport aircraft reveals striations that occur in pairs, each time a small and large striation together. The two major loads on this flap beam relate to the opening of the flaps, which are partly out at takeoff and fully out while landing. Hence the landing imposes the largest load cycle and the largest striations. The macroscopic difference in appearance can be illustrated with this example where a helicopter rotor blade separated due to fatigue. Blade failure occurred in a section with a lightning hole in the spar of the blade, with a rivet hole at the top and the bottom of it, with the hole and the cracks left reveal no macroscopic plastic deformation, while the right side clearly indicates the presence of plasticity by ovalization of the hole. The growth bands should not be confused with striations, which are microscopic little ridges on the surface. The growth bands are visible with the naked eye and relate to the load spectrum applied. As mentioned earlier, the fracture surface is not entirely flat, hence little deflections in the fracture plane will reflect light differently. This little difference in reflection is visible as growth bands. Although growth of cracks occurs mainly perpendicular to the principal stresses, in thin sheets and plates one may observe shear lips at the surface. At the surface, plastic deformation is less restrained, which allows the fracture surface to tilt to 45 degrees towards the surface. This forms shear lips at the surface, which for thin sheets may result in complete tilting of the fracture plane. In summary, in fatigue in metal, cyclic slip results in the formation of cracks where the initial phase is dominated by surface conditions. Once the crack has propagated further, the material's resistance is governed by bulk material properties. The fatigue limit represents a limit to fatigue failure. Initiation of microscopic cracks may still occur below the limit, and the effect of environment will be dealt with in a later learning unit of this course, but it clearly influences both the initiation and propagation phase. Fracture surfaces contain information on the fatigue loading applied, which can be studied with electron microscopes.